So here, involving bonds, we want to know which of the following be the strongest bond. And what you have to remember is that bond strength is the inverse of bond length. So what do I mean by this? I mean that the stronger the bond is, the shorter the bond is. So if something is a very strong bond, it's going to have a small bond length associated with it, because that means the atoms are closer together. It's harder to break the bond. So bond strength, bond length are inverses of one another. So longer the bond, the weaker the bond, which makes sense because it's easier to break. Now, in addition to that, the way we can determine the strength of a bond is by looking at the difference in electronegativity of the bonds when we're comparing apples and apples. What do I mean by apples and apples? I mean that we're comparing, for example, all single bonds. The only difference is the atoms are changing, for example. In that case, we can look at electronegativity difference, and the more polar the bond, the stronger the bond is. So now if we look at the electronegativity difference of all these bonds, we see that in N, well, that has electronegativity difference of 0. It's a nonpolar bond. Nitrogen selenium bond, electronegativity difference of 0.6. It's polar. Now you may think, well, fluorine is the most electronegative element on the periodic table, so obviously the nitrogen-fluorine bond should be the most polar bond. However, you'll notice that nitrogen and fluorine are somewhat close to each other, and so their difference is only 1, which is a polar bond. But if we look at nitrogen and silicon, we see that the electronegativity difference is 2.1. And then finally, nitrogen and iodine is 0.5. So based on this, we can determine that the nitrogen-silicon bond is the most polar, therefore it's going to be the strongest bond. So that's the strongest bond. Now, if we were to rank these from strongest to weakest, if you're interested, of course, this one would be the strongest, 1 being the strongest. The second strongest would be the nitrogen-fluorine bond, and then nitrogen-selenium, nitrogen-iodine. See, they're going and decreasing electronegativity, and then lastly, the nitrogen-nitrogen bond. So again, when you have a series of similar bonds, just different atoms, the way we determine that is by looking at the difference in electronegativity. The greater the electronegativity, the stronger the bond. Now moving to a calculation here, we want to calculate delta H of reaction using the bond enthalpies for the chlorination of methane to form chloroform and hydrogen gas. And so sometimes it's hard to visualize the types of bonds present by looking at the reactants and products. So whenever you're asked to determine the delta H using bond enthalpies, the first thing I would recommend is write the Lewis structures or draw the Lewis structures of the reactants and products. And this will give you an idea of the types of bonds that are broken and the types of bonds that are formed, because every type of bond has a different bond energy associated with it. And so to calculate delta H of reaction, it's the sum of the bond energy of the reactant bonds broken minus the sum of the bond energies of the product bonds formed. And so from this, we can get delta H of reaction. So from the chemical equation, we see that we have 8 carbon-hydrogen single bonds, because again, we have 2 molecules of methane. Each molecule has 4 CH bonds, so that's a total of 8 CH bonds. Then we have 3 chlorine molecules, so that's a total of 3 chlorine-chlorine bonds. And on the product side, we have 2 molecules of chloroform, so that means we have 2 CH bonds, 6 carbon-chlorine single bonds, and 3 hydrogen-hydrogen single bonds. So now we know what we're adding and subtracting. We can put in their bond enthalpies and determine the difference. And so here, the difference is negative 135. So that's the delta H of this reaction. It's an exothermic reaction. So whenever you have an exothermic reaction, this tells you that the bonds of the products are more stable than the bonds of the reactants. So very commonly when you want to calculate delta H of reaction, typically we do it for combustion reactions. So using the bond enthalpies, can we calculate the delta H of this combustion reaction, which is the combustion of 2-butene to give CO2 and water. Now, one thing you have to note is that the carbon-oxygen double bond in CO2 has a different bond enthalpy. Usually it's an asterisk or it's in its own little slot than a normal carbon-oxygen double bond. So again, CO2 has its own special CO double bond energy. So again, the best thing to do is to draw the Lewis structures of each. So 2-butene looks like this. I apologize for the unevenness. But you see we have carbon-carbon single bonds, carbon-hydrogen single bonds, carbon-carbon double bonds, oxygen-oxygen double bonds, carbon-oxygen double bonds, and oxygen-hydrogen single bonds. So now we sum up all the individual bonds, and we're going to take the sum of the bond energies of the reactants minus the bond energies of the products. And so we have 8 carbon-hydrogen single bonds. So there's 3, 4, 5, 8. We have 2 carbon-carbon single bonds, 1 carbon-carbon double bond, 6 oxygen-oxygen double bonds, 8 carbon-oxygen double bonds, and 8 OH bonds. So now we know the types of bonds and their numbers. We can enter the bond enthalpies and determine the difference. So here we get a negative 2,546. So again, what that means is that since this is exothermic, the bonds in the products are more stable than the bonds in the reactants. So now a different take on delta H with bond enthalpies. In this problem, we want to calculate the bond energy of an NO in NO given the following reaction. And it gives us the delta H of reaction is 180 kilojoules per mole. So we want to know if we take the synthesis of NO, what's the bond energy of the NO bond in the product? And we're given delta H. So again, delta H is the sum of the bond energies of the reactants broken minus the bond energies of the product bonds in the products formed. So we'll see we have 1 nitrogen-nitrogen triple bond, 1 oxygen-oxygen double bond, and then we have 2 of the NO molecules. So we're going to have 2 NO bonds. We plug in delta H, we plug in the bond enthalpies for the reactants. We rearrange it, combine, we get 2 times the bond enthalpy of NO is 1256. And you see that the bond energy of NO is 628. So again, when a reaction is endothermic, it tells you the bonds of the reactants are more stable than the bonds of the products. So one last thing we discuss in this series of chapters is sigma and pi bonds. So just to give you kind of a brief explanation of both, sigma and pi bonds are what are found in single, double, and triple bonds. First, I'm going to tell you what are found in each one. So a single bond contains one sigma bond. And what does a sigma bond look like? So if I was to draw you an illustration of a sigma bond, so let's say we have two atoms. We'll label them, for example, X. So X is two atoms. What a sigma bond is a lobe of electron density between the two atoms. So this cylindrical lobe of electron density is a sigma bond. So it's a different way of expressing what a single bond is. We call it a sigma bond. So again, a sigma bond is a cylindrical lobe of electron density between two atoms in a molecule. So this is a sigma illustration of a sigma bond. So all single bonds are sigma bonds. Next we go to double bond. A double bond contains one sigma bond and one what we call pi bond. Because remember, a double bond has 4 electrons. A single bond has 2 electrons. So you see the difference. So with a double bond, these pi bonds, if we draw 2 atoms, so 2 atoms X. So again, the sigma bond is the cylindrical lobe of electron density between the 2 atoms. And then the pi bond is a lobe of electron density above and below the sigma bond. So again, the gold is a pi bond, the green is a sigma bond, and both of these combined make up a double bond. So remember, a double bond once has 4 electrons, therefore there are 2 electrons in the pi bond and there are 2 electrons in the sigma bond. And then lastly, we have a triple bond. And as you can imagine, a triple bond contains one sigma bond and 2 pi bonds. And that's a total of 6 electrons. Just like we say, triple bonds have 6 electrons between them. So now if I draw 2 atoms identified as X, so again, the sigma bond is the lobe of electron density between the 2 atoms. That's sigma. And then we have the pi bond above and below. In addition, since we have 2 pi bonds, and this is hard to do in 3 dimensions, but there's another pi bond as well above and below. So the green and the red represent 2 different pi bonds. So that's a total of 6 electrons. So now when we go through this, we got to count all the bonds to get the number of sigma bonds, and then we count the number of pi bonds by looking at the multiple bonds. So we'll do the pi bonds first. So a double bond has 1 pi bond. So there's 2 right there, and a triple bond has 2. So the number of pi bonds equals 4. Now for the sigma bonds, we have to count every bond. So here we have 3 carbon-hydrogen bonds. So that's 3, 4, 6, 7, 8, 9, 10, 12, 13, 14, 15, 17, 18, 19. And so there are 19 sigma bonds. And so that's how you determine the number of sigma and pi bonds in a molecule, is by looking at, for sigma bonds, all the bonds present. And for pi bonds, just look at the ones that have multiple bonds. And then one kind of application of bond energy. So here we're given that the oxygen-oxygen single bond has a bond energy of 146. An iodine-iodine bond has a bond energy of 149. What would the approximate bond energy of the oxygen-iodine bond be? And it gives us the electronegativity value. So here we're not supposed to go and look on Mr. Google to see what the bond energy is. We have to use the information given to us in this problem to elucidate what the approximate bond energy would be. And so what we have to remember is that for nonpolar bonds, or a hetero atom nonpolar bond, so hetero atom means two different atoms in the bond. The bond energy is approximately the average of the two homonuclear bonds. So for example, we all know that the carbon-hydrogen bond is a very classic nonpolar bond. So if you take the carbon-carbon single bond, the hydrogen-hydrogen single bond energies, add them together, take the average, that would give you an approximation of what the carbon-hydrogen bond energy would be. So that's what we mean by when we have a heteroatom nonpolar bond, the bond energy is approximately the average of the two homonuclear bonds. Because it's nonpolar, the electrons are shared equally. Now for a heteroatom, I forgot how to spell hetero. Polar bond, the bond energy is greater than the average of the two homonuclear, oh, I forgot an E. Bonds. So if you have a polar bond, the bond energy of that heteroatom polar bond is going to be greater than the average. And so the more polar it is, the greater the bond energy is above the average. So what we have to do is to determine is an oxygen iodine bond a polar bond or a nonpolar bond. If it's a nonpolar bond, then the bond energy of that bond would be approximately the average of the two homonuclear bond energies. If we determine that it's a polar bond, then we find what the average is, and we can approximate to say that the bond energy would be greater than the average. And the more polar it is, the greater it is above the average, because that means that the electrons, the more polar it is, the electrons are shared more unequally between the two atoms. So if we look at the difference in electronegativity, we have 3.5 minus 2.5. That's an electronegativity difference of 1. So this is a polar bond. So since it's a polar bond, it would be greater than the average of the two values. So therefore, it would be C. Again, this is an approximation method. It won't be exactly what it is in the table, just a way to approximate what the bond energy should be.